Hello everybody. Today I forgot to press the record button, and so this lecture 6 is just a reproduction of what I told today during the class. So the lecture 6 is about the proof of our main theorem in topology. So remember that we had the projective variety X, hyperplane section Y, hyperplane section Z, their intersection X prime, and then we took U X minus Z and Y minus X prime, basically throwing away Z. So the main theorem was that the cohomologies of U with boundaries in V are 0 except in dimension n is the dimension of X, and for Q equal to n, these are free Z modules. Okay, so let's start the proof. Since this is a second version of lecture 6, it will be faster. I hope I will not forget next lecture the recording. Okay, so I recall that by Veronese embedding, instead of hyperplane sections, we can talk about hypersurface sections. And so if we take homogeneous polynomials fg and c with complex coefficient x0, xn variables, then y can be f equal to 0. Actually, there is a misprint here. So y will be at the hypersurface if equal to 0 intersected with x, and z will be hypersurface g equal to 0 intersected with x. So I will take polynomials of degree a and b. Degree f will be a, degree g will be b, and everything intersecting everything else transversely. Okay, let's go. So in order to prove the main theorem, I need the notion of fibration. So I will take greatest common divisor as AB equal to D. I will divide A by D and B by D, and then I will call this Q, the other one P. And so if I form this quotient, then upstairs and downstairs we have this homogeneous polynomial of the same degree. So this will induce a holomorphic function from Pn minus the indeterminacy points, which are these, because for fg equals 0, we have 0 over 0, to P1, which is C union with infinity. So g equal to 0 will correspond to the value infinity here. So we have to restrict this f. Let's say f equal to fp divided by gq to our variety x. So when we restrict it, this indeterminacy points is the same as x prime. And then we will have a map, holomorphic map from x minus x prime to P1. And okay, two examples of this situation are useful to carry in mind. The first one is the Lefschetz pencil case, in which we take PQ equal to 1 and AA and B equal to 1. Which are that in this case f and g are just linear polynomials. So this corresponds to classical hyperplane section. But another example which is very useful, and it is inspired by some works in singularity theory, the case in which X itself is the projective space Pn, Z is the x0 equal to 0. This is a kind of Pn minus 1 at infinity, and Y is given by a homogeneous polynomial equal to 0 of arbitrary degree. Okay. This second case leads us to the notion of tame polynomial, which is fairly discussed in my book, and as I said, this case I started to write it in my book because of some applications in holomorphic foliations, and its origin comes from singularity theory by Arnold, Gusendzad, Varshenko, Pham, and many others from 1950s to 1980s, 90s, that the people developed this. And Milnor, of course, then there will be Milnor number in our study. Okay, so either case you take, let's continue. So then we take this fibration. We are looking for, we will look for the fibers of f equal to c, and so this will be these kind of hypersurfaces. And from now on, just remember that, okay, then we always restrict to x. So this, at the end of the day, this is intersected with x. Okay, so by our notation z, and actually by z minus x prime will be the fiber at infinity. We will remove the fiber at infinity from our notation. The y will correspond to the fiber 0, y equal to f minus 1, 0. And let's introduce more notation. So for any subset k of c, Lk will be f minus 1 of the set k. And when the set k is equal to just a point, Lb will be just the fiber over b, fiber of f over b, f minus 1b. Okay. And by some reason that you will see in the proof, we will just consider the case p equal to 1. So our pencils will be of the form f divided by g equals to the q. In our second example, g will be just x0, and in our first example, q will be also 1, and yeah. Okay, so let's go to the second page. So as you see, there is no audience for this lecture. I'm doing it alone. Okay. So our main theorem will be reduced to this statement. So when we remove x is z from x, the whole space U, which is also x minus z, will be LC, and the point over 0 is just v. This is y minus x prime. And something that would be useful from now on, I will use just arbitrary value. So I will put b equal to 0, but from now on b will be I will use the notation b. Okay, so now what next we need? We need the set of critical values of f in C. I will denote it by C1, the set C1, C2, C mu. This is our assumption b is not a critical value, it is a regular value, so b doesn't belong to the set. Maybe very fast to remember what is a critical value and critical point. So the critical value P is just the point such that the derivation of f, which will be from tangent space of u at P to tangent space of C at actually there is a mistake here. This will be Fp. The tangent space of u at P, from tangent space of u at P to tangent space C at Fp, this derivation will be 0 if P is a critical point. And so by definition, critical value is just the f of the critical point. And okay, so what else? Okay, so something in the next lecture I will discuss is this Ehresmann's fibration theorem. Today I will just mention its consequence. So this Ehresmann's fibration theorem, whatever it is, together with all our transversality hypothesis, will imply that f as a function from u to c is a C infinity fibration over C complex numbers minus critical values. And in the classical Ehresmann's theorem, we have compact fineness, compact fibers, properness, and so on. Next year I will come to this theorem. But for now, I want just to say what it is, this implication. So this is as follows. For any point B of B, regular value, which is outside C minus C, which is in C minus C, it has a small neighborhood U, such that we have this this diagram. So what is this diagram? We have f minus u. We must have isomorphism, C infinity isomorphism between f minus u and u, u times f minus 1b. And what else? From here to here we have the f map. From here to here we have the projection on u map. Both of them are, let's say, are fibration. So this means that this diagram must commute, and in some sense this means that we are trivializing this fiber bundle locally. In particular, if we so this commutes. And in particular, for example, if we take another point, let's say f b tilde here, so this is over u, this is b, this is u. If we take another point, this map will induce isomorphism between f minus 1 b tilde and f minus 1b. So in some sense, this theorem says that in the category of C infinity manifold, if we consider our complex, our algebraic varieties, complex manifolds in this category of C infinity manifolds, then all the fibers are the same. They are isomorphic. And the only atypical fibers might be fibers over C1, C2 until C more. Okay, so in next lecture, I will talk about this Ehresmann's fibration theorem a little bit in order to do Picard-Lefschetz theory. So once this is done, the proof of our main theorem is a kind of classical exercise in algebraic topology using some bunch of axioms of cohomology theory. So maybe now that this is a reproduction of lecture 6, it will be faster. Maybe I tell the reference, the place in my book. Okay. So from now on, the rest of the proof will be just this the details of the proof of theorem 6.4 in my my Hodge theory book. So as you see with our new language, our new notation of the theorem is this one. So the relative cohomology, let's try to write in the cohomology, HK. So this LC, you know, it is C is P1 minus infinity. So HK is 0 for a k not equal to n. And it is freely generated Z modular of rank R for k equal to n. And during the proof, we will discover what is this R. And in order to see what is this R, we will define the Milnor number of singularities. And R will be the sum of Milnor number of all singularities that will pop up in our way. But this part, the idea is to learn its details end of this lecture and also starting the next lecture. Okay, so let's go back to the proof. Okay, so first I have to explain this picture. Maybe I explain this picture in my own book so that this lecture becomes different from the one today I talked. Just a moment, where it is. Okay. Present now. Okay, so maybe I explain it here on my book. So we had this regular point B. We had let's say C1 critical value, C2 critical value, C3 critical value. So it must be point here, and the C4 critical value. So first we connect a B to C1, C2, C3 in such a way that all these lambda i's, they do not intersect each other except at their initial point B. So if you want, you can continue the path further until C3. It will not change our discussion. Okay, and moreover, we produce small disks, very small disks of radius epsilon, let's say, around each CI. So small disk D1, D2, D3, and D4. And for simplicity, just suppose that everything closed. I mean, all disks are closed, and these lambda i's are so closed, so they contain the end and the starting point. So this is called in singularity theory a distinguished set of passes, which all in it also requires that we give an order to this lambda i's. But for our proof, for the moment, we will not need this order, and just the topological picture will matter for us. Okay, so once we do this picture, so the first observation is that the whole complex domain together with the point B can be retracted to this picture to get it to point B. So let's say that I will put K equal to union of all these lambda I and the union. I switch between the notion of path and its image. So here it means the image of lambda I actually, union with all these di. Sorry, there is no more union. Okay, let's see. So, okay, then actually the union of di, union with union of lambda I. So the first observation is that the whole complex plane together with B can be contracted this picture, fixing the point B. And well, of course, this is intuitionally it's okay, but in topology we write precisely what is retraction and so on. Okay, so let's come back to the page. So as I said, let's take I equal to lambda I union with di, k, the union of all these ki's. And so k together with b is a deformation retractor of C and B. And okay. So it is a kind of a classical fact in topology that if you have a retraction and over this retraction you have a fiber bundle map, in our case we have this fiber bundle map, then this retraction can be lifted up to retraction upstairs. This means that LK and LB will be the deformation retract of LC, LB. And we can assume that in this retraction, the points of LB are fixed; they do not move. Maybe one picture of this retraction. For example, if we have just two critical values, just imagine that every neighborhood of this picture is each time decreasing and getting near to this union of these two disks together with these passes. Okay, so here comes another statement from algebraic topology, that if LK, LB is a deformation retract of LC and BLB, if we have a pair of topological spaces, one is the deformation retract of the other one, then nothing changes in cohomology. And this means that HQLCLB will be the same as HQLKLB. So remember that we wanted to compute this cohomology. And so our computation is reduced to compute this cohomology. Now it comes another application of homotopy axiom for cohomology. We can replace LB with this one. Let's say lambda tilde. We can replace LB. Okay, and then maybe before telling this one, so then I have to say lambda tilde. So now let's a little bit thicken this point B to some small neighborhood here. So and in each pass, maybe just take lambda a small piece. Let's say lambda I tilde, and then just take the union of these things. So I will define lambda tilde, maybe just a small neighborhood of B inside this K space. Since it is a small neighborhood, it will not intersect D1, D2, and DMO. So we can replace LB with this L lambda tilde. And the reason is as before. And the point is that it is written here. LB is a deformation retract of lambda tilde. And the reason is exactly that KB is a deformation retract of K lambda tilde. Since this lambda tilde, it is just a union of mu passes intersecting in B. It is simply connected, so it can be contracted to point B. So again, this contraction will be lifted up to the fiber bundle map, so we will have this statement here. So this is the second time we use this theorem. Okay, so let's go further. And the reason that we want to we did this one, because we want to break down this cohomology into many other smaller cohomologies attached to each CI. And once we do this one, now we can use Excision Theorem. Excision Theorem. So by our choice, the topological closure of okay, let me say, okay, so I have to do define a, so what I will do, I will take even a smaller neighborhood of B inside this lambda tilde. This means that if, for example, if lambda tilde I goes until here, I will take even a smaller neighborhood, and then I will define this lambda double tilde inside lambda tilde, such that at the end, the algebraic, the closure of lambda double tilde is inside L tilde. Once this is done, I can, Excision Theorem says that whenever you have a relative cohomology and you have something inside here whose closure is still inside there, then you can cut this L double tilde lambda. And so the Excision Theorem will tell you that this we get our cohomology now will become this cohomology. And why we did this one? Because once we do this one, we cut this L double tilde lambda. This set, our picture that we had will be a union of mu connected spaces, and in particular, the same things for this one will happen. So what will happen? Our cohomology will be isomorphic to HQL DI LBI. And what are these BI? Let me explain this one. So once you cut L double tilde lambda, then you will have, let's say, union of cohomologies of this whole guy with boundaries here. But this boundary here, which is a interval, can be retracted to the point BI, which is the intersection of lambda I with DI. So at the end of the day, we will have this union HQ LDI LBI. And okay. And if something from now on we will need it, that our original F has isolated singularities. And I gave a sketch of the proof. Let me say a few words before going into this one. Yeah, so now our theorem is reduced to study these cohomologies, and these cohomologies has mixed local and global aspects. It is local in the sense that we are now dealing around the small disks, around critical value CIs, and we take BI in the boundary of the disk. We take these relative cohomologies. but it has a global aspects because the fibers are still global affine varieties. Okay, so basically today I reached to the proof of this statement. So maybe I skip the proof of this one for the next lecture, in which I will put maybe more details. And next lecture, what we are going to do, we have to analyze this one. What we have to do, we will take a sphere of dimension 2n-1. Remember that our ambient space is n-dimensional, so it's it is like locally it's like Cn. So we will take spheres of the 2n-1 dimension, which intersects our fibers transversely. In this way, we will get rid of these global aspects of this cohomology by cutting out outside this sphere, and we will be reduced to the local study of fibration and singularity theory. And that's why these are, in a local context, these are called Milnor fibration. Milnor vibration. And okay, so since this lecture is I'm repeating for the second time, so as I said, this will be shorter. It was just for the sake of completeness in YouTube. It's not so good. It's not so good to have lecture 5 and then suddenly jumping to lecture 7. And okay, the next lecture I will talk about this one and the rest of the proof of our main theorem, will using some facts from singularity theory. And in the next lecture we will have the concept of Lefschetz thimble and Lefschetz vanishing cycles around this critical point P. Okay, I think just for the sake of reproducing the main content of the course, it is enough. So let's just stop.